Hey, hello. I'm just doing this so I'm studying by saying all this stuff out loud, and also hopefully I'll play it as I go to sleep and sleep throughout the night, and maybe I'll learn this stuff through subliminal messaging, or as I like to say, osmosis of the sound waves. Just a little overview of what this video, I guess, is about. This is for algebraic structures, i.e., abstract algebra. And I'm just going through the Quizlet that I have so far, which is on section 7.2, section 7.3, and section 7.4. So I guess let's get into it. Okay. Mm, Okay. So starting with whatever section she wanted to start with, kind of section 7.2, we've got theorem 7.5, which says that we should let G be a group and the elements A, B, and C belong to G. Then we can say that G has a unique identity element, which we can oftentimes just call E or E sub G, big G. So E sub capital G. We can also say if AB equals AC, then B equals C. And we can also say if BA equals CA, then B equals C. So even if this is an abelian group, you can still do like you can still do that. And finally, when G is a group, each element of G has a unique inverse, which we know from our four group axioms. Corollary 7.6, let G be a group and let the elements A and B belong to G. Then we have the Sachs-Hughes property, which is quantity AB inverse is B inverse, A inverse. So you've got to flip them and then distribute the inverse. And A inverse inverse is just A. Um, So especially for that Sachs-Hughes for non-abelian groups, again, AB quantity AB inverse does not equal A inverse B inverse. It's got to be the flip. But for abelian groups, you can just say that because when you do the flip, since it's abelian, you can just flip it back to A inverse B inverse. So you could just go ahead and automatically say that, but I always like to just go ahead and show that. Um, Also, anytime we've got an element to a power, that's just like the amount of times that element is multiplied, or in the case of an additive group, added. You can also say a to the 0 is just e, and a to the negative n is a inverse n times, or vice versa, a to the n, a n times, and then inverse that. Theorem 7.7, let G be a group and let the element A belong to G. Then for all elements K, M, N in the infinite set of integers Z, with K being greater than 0, so K is positive, you can say A to the K raised to the inverse is A inverse raised to the K, i.e. A raised to the negative K. You can also say for any a to the m times a to the n, that's a to the m plus n, like your exponent rules. And similarly, a to the m raised to the n is a raised to the mn. Order of an element. The order of an element G in a group G is the smallest positive integer n, such that g to the n is e. In additive notation, that would be ng equals 0, since in addition, the identity is 0. If no such positive integer exists, we say that g has infinite order. The order of an element g is denoted by a bar g bar. So that's like cardinality of g, or absolute value of little g. But important thing here is that order g is not only a positive integer, but it's the smallest one. It's the smallest positive integer that does this, is the order. Order of a group is the number of elements in a group. So that's much simpler. That's basically just cardinality again. Theorem 7.9. Let G be a group and let A belong to G, and let A have a finite order of n. Then we can say A to the k is E if and only if n divides k. Also that A to the I equals, I think I meant to say A to the j. So A to the I equals A to the j if and only if I is congruent to j mod n, where n is that order. And finally, if n equals td, where d is greater than or equal to 1, then A to the t has order d. So that's just kind of like more like helpful simplifying rules than anything. Corollary 7.10. Suppose G is an abelian group where every element has finite order. Then we can say if C belongs to G is an element of the largest order in G, then the order of every element of G divides the order of C. i.e., the element of largest order in G means that if order of A is less than or equal to order of C for all A and G. Oh, yeah, that's not that didn't, I didn't need an if there. That's not logical, but so element of largest order in G, once we find that tells us that the order of any other element in G is either less than or equal to the order of the largest element order. Subgroup definition. Non-empty subsets of a group that are groups with respect to the binary operations of the mother group. So a non-empty subset H of a group G is a subgroup of G if H itself is a group under the binary operation of G. You can also say it's a subgroup if H is a group on its own. So every group has at least two subgroups. That's important to know. The trivial subgroup, set E, or the entire group G. So there are like there are always two subgroups. So you can't say suppose H is a subgroup of G. Like showing that H is not empty is pretty easy because you can just say H at least has E in it. Which we'll see in a minute why it has to have E for sure. If H is a subgroup of G such that H does not equal G, then H is called a proper subgroup. So that's kind of similar to the proper subset. So that's some notation. The kind of H is less than or equal to G. So what we're used to seeing as subset notation, that's actually now subgroup. And H with like just the thicker version of the subset is that's just subset now. Theorem 7.11. Here's one of the ways we can show something is a subgroup. A non-empty subset H of a group G is a subgroup of G if and only if the following hold. So kind of before number one, we say oh my gosh, it's 11:39 p.m. so I'm tired. We have to show H is not empty, which I just said earlier would be super easy. And you also have to show again that H is a subset of G. And then you have to show if two elements A and B are in H, you have to show then that AB belongs to H, meaning that H is just closed under the inherited operation from G. After that, then you say if A belongs to H, then you have to show that the inverse of A belongs to H for all A. Theorem 7.11 star kind of does, so instead of that being like 4 steps, kind of does it in 3. So again, show that H is non-empty and show that it's a subset of a group of a group G. And then you can do closure and the inverse at the same time with showing that H is a subgroup of G if and only if A star B inverse belongs to H for all A, B, and H. How do we check if a given set is a subgroup? Check for non-empty, check that it's a subset, then use theorem 711 or 711 star. Or you can use 712 if G is a finite group. So useful if, or sorry, you can use 712 if the order of H is finite. So let H be a non-empty finite subset of a group G. If H is closed under the operation in G, then H is a subgroup of G. So that'd be a really helpful one if it was convenient to use, but if you'd have to show that order of H is finite, then it's not worth it. You might as well use 711. Center of a group Z of G, that's the subset of all the A's in G where A commutes with sorry. Hello? Oh, that was still going. Okay. Excuse me. So center of a group G is the subset Z of G that contains all of the elements in G that commute with every element in G. So when G is abelian, the Z of G is G, because all of the elements commute with one another. When G is not abelian, then Z of G is not all of G, so Z of G would then be a proper subset of G. Cyclic groups. Suppose G is a group and let an element A belong to G. Let what would you call that? Side caret A denote the set of all powers of A, where side caret A equals the set A all of the integers, meaning set of A to the n where n belongs to infinite set of integers, and where the order of A equals the order of that cyclic group. So side caret A, those powers generate all of the things in A in the congruence class A. Where since we dropped the bar notation, so A is A bar. Cyclic group A is not empty since A belongs to cyclic group A for n equals 1. And also important to note, like from earlier, what was that? Theorem 7 or 7-8, where I said that's just helpful reducing stuff. But when n is 0, A is E, I'm pretty sure. So important to note. Different elements of a group may generate the same cyclic subgroup. And so if we're asked, is blank a cyclic group? What we're really trying to answer is there an element A in G or whatever group such that G equals that cyclic group A. Finally, let G be a group and let A belong to G. If the order of A is n, then the order of A inverse is n. Cyclic groups examples, some infinite ones, Z plus as a generator of 1, E plus meaning even numbers under addition. That's an infinite cyclic group with a generator of 2. Some finite ones, Zn plus, that's an abelian finite cyclic group. And U10 has an order of 4 with generators of 3 and 7. And so far, I haven't written down any non-cyclic ones yet. To reiterate, what is A, meaning sidebar or side caret? For additive groups, A is the set NA for all N and Z. And for literally every other kind of group that's not specified being additive, that would be the set A to the N for all N and Z. So you literally only use the additive notation if you're explicitly told this is an additive group, or you know it's one. Like if the group was just Z and you were finding the generator for that. Meant to put something there. All right, theorem 7.14. Cyclic group of A is a subgroup of G. That's basically what it is. So the actual theorem says if G is a group and A belongs to G, then the cyclic group of A is the set A to the N for all N and Z. That cyclic group A is a subgroup of G. So I didn't even need to read out that whole sentence because that first little blurb at the top basically says it. Theorem 715 and its additive version. Let G be a group and let A belong to G. You can say then if A has infinite order, then the cyclic group of A is an infinite subgroup consisting of all of distinct elements of A to the K with K in Z. And conversely, if A has finite order, then the cyclic group of A is a subgroup of order n. And the cyclic group of A is the set A to the 0, where A to the 0 is E, like we said before. So it's the set A to the 0, A to the 1, A squared, all the way up to A to the n minus 1. And you can use theorem 7.9 part 2 to help prove this, where A to the I equals A to the n. And the additive version of that, if A is infinite order, then cyclic group of A is an infinite subgroup consisting of the distinct elements Ka, where K is an integer. So definitely remember for both of these infinite order distinct elements. Additive version for finite order, cyclic group of A is a subgroup of order n, where the cyclic group of A is 0A, 2A, blah, 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 all the way up to n minus 1 times A, where 0 there is there because that's the identity. All right, theorem 717. Every subgroup of a cyclic group is itself cyclic. So if H equals E, like the set E, then H is the cyclic subgroup generated by E, i.e. H equals side caret E. If H does not equal E, then H contains a non-identity element of G, say A to the I, with I being non-zero. Theorem 718. Oop. How do we determine if a given group is cyclic or not? All right. Finally, the actual material on this exam. What's an isomorphism? Let G and H be two groups, we say that G is isomorphic to H if there exists a function f that maps G to H such that f is a well-defined function, f is injective or one-to-one, f is surjective or on-to, and f is operation preserving or a homomorphism. In other words, an isomorphism is a bijective homomorphism. Isomorphism, checking well-definedness, we do this by saying if f mapping G to H is well oh my gosh, not if. F mapping G to H is well defined when G1 equals G2 and G implies that f of G1 equals f of G2 and H. And conversely, if f of G1 doesn't equal f of G2 and H, then G1 cannot equal G2 and G. Checking one-to-one and isomorphisms, I still need to find the actual thing in that, but I know how to do that. Isomorphism, checking on two, i.e. surjectivity. We let K be an element belonging to H, and then we want to find for all J in G that f of J equals K in H. Checking homo, let J and K belong to G, then f of JK equals f of J, f of K in H for all fk in G. Iso versus homo. All isomorphisms are homomorphisms, but not all homomorphisms are isomorphisms, i.e. homomorphisms can fail injectivity and or surjectivity. Isomorphism examples, rotations of D4 are isomorphic to Z4, cyclic group of 3, where that cyclic group of 3 is in rationals without 0. That is isomorphic to the infinite set of integers. U5 is iso to Z4, and Z4 is iso to U5. The rotations of D4 are they're iso to U5, and R is iso to Z4. And using the Cayley-theorem, A of G is isomorphic to Sn when the order of G is n. Homomorphism examples, just one I put down, is F mapping rationals without 0 to rationals without 0, defined by f of x equals x squared. That's a homomorphism. It ended up failing surjectivity and I think injectivity. And then some examples that are neither isomorphic or homomorphic. S3 and Z6 are not isomorphic to one another. They failed something. And Z4 and Z2 cross Z2 are also not isomorphic to one another. Some remarks about isomorphism. Let G and H be two finite groups, where order of G is n and order of H is m. If n does not equal m, then G cannot be isomorphic to H. But if the order of G equals the order of H, that still doesn't necessarily mean G is isomorphic to H. So you need the orders to equal for the possibility of the isomorphism relation even occurring. But just because they're equal doesn't necessarily mean it will happen. So an example where those orders are the same, but they aren't isomorphic is S3 and Z6. Also, if F is an isomorphism, I think I meant to say if, interesting. Like F is a function for an isomorphism, then an element A and G and an element F of A in H have the same orders. So that's kind of that same thing from the top, basically, but applying it to the elements. And also I wanted to note here that transitivity applies for isomorphism, as well as like for the subgroups. So if A is isomorphic to B and B is isomorphic to C, then A is isomorphic to C. Automorphism. That's an isomorphism from a group to itself. To prove, you have to check if F is an isomorphism. F if oh my gosh. F is an isomorphism from G to G. Theorem 719. If G is a cyclic group, then if the order of G is infinite, then G is isomorphic to the set of integers. And if the order of G is finite of order n, then G is isomorphic to Zn. And also I wrote here that G as a cyclic group, as a reminder, means G is side caret A, which is the set of all a to the k for k in integers. So again, if G is a cyclic group has infinite order, it's isomorphic to Z. If its order is finite, then that number for the order is the sub little unit of Z that G is isomorphic to. Image of a function. Image of a function f mapping G to H is a subset of H. Namely, image of f is the set of all H in H such that H equals f of A for some A in G. Also, you can rewrite this as the set of all f of A for all for A and G, which we want to remember still is a subset of H. Image of a function examples. E plus, those even integers, that's a subset of Z plus. So E is a subset of Z. That's just kind of a warm-up example. F mapping Z to Z, where f of n is 2n for all n and Z. Image of f there would be the set of 2n for n and Z. So E is a subset of Z. But note that this image of f doesn't actually equal Z, since the subset doesn't work the other way around. And kind of similarly, f mapping rationals without 0 to rationals without 0 for a function f of x equals x squared. That ends up being the set of x squared in rationals without 0 for all x in rationals without 0, which is actually ends up being positive rationals, which is a subset of rationals without 0. But again, doesn't work the other way around with the subsets. Image of f ends up not equaling rationals without 0 here. Image of f remarks. Function f can be considered as a surjective map from G to image of f. So f mapping G to image of f is going to be a surjective function since every element in image of f is automatically an output. So that's something to think about, maybe going back to that definition of surjectivity. Theorem 720, let G and H be two groups with identity elements E sub G and E sub H, which I'll just say EG and EH. If F maps G to H is a homomorphism, then we can say four things. F of EG equals EH, because if it's a homomorphism, then they're two groups that share the same identity element. So even just doing that mapping, it's still going to be the same identity element. So f of EG equals EH. So also it's just some other things you can say. F of A inverse equals the inverse of f of A for any A and G. Also, you can say the image of f is a subgroup of H. So not only is it a subset of H, but when G to H is a homomorphism, the image of f is a subgroup of H. And finally, if f is injective, then G is isomorphic to image of f. So going back to that definition of one-to-oneness, which I need to put in here. If F is an injective homomorphism, then G is then isomorphic to image of F. So that kind of works out in a different way. All right. Whew. Kind of something that she wanted us to start thinking about, which I need to fill out in here. Going back to that part 3, saying image of F is a subgroup of H when F mapping G to H is a homomorphism. When can we say the image of F then is a normal subgroup of H? Moving on for now, Cayley's theorem, also known as theorem 721. Every group G is isomorphic to a group of permutations, where permutations are defined as bijective functions from G to G. So here, let G be a group. Consider A of G, which is the set the set F mapping G to G, where F is a bijection. Here, A of G, we also want to suppose that G is not necessarily a homomorphism. Then we can say A of G still consists of all one-to-one and onto functions from G to G, where A of G is a group with composition as the operation of G. Cayleystheorem example. This is like one that I put back in the isomorphism examples. We can say S of n is the set F, the set where F maps T to T, and F is a bijection, and T is just the natural numbers. Here, A of G is isomorphic to S of n, where the order of G is n. Corollary 722. Every finite group G of order n is isomorphic to a subgroup of the symmetric group Sn, meaning with the order of G equaling n, then A of G is isomorphic to Sn. And from the Cayley's theorem proof, this works out because we showed G is isomorphic to image of F, and image of F is a subgroup of A of G, and A of G is isomorphic to Sn. So then we apply transitivity to say that every finite group G of order n is isomorphic to a subgroup of the symmetric group Sn. And an example of this, let's say G is Z3, which is a group of order 3, which is also an additive group, by the way. Then G is isomorphic to a subgroup of S3, and I need to figure out what subgroup that is, but it's just like G would be isomorphic to either like 1, 2, 3, 2, 1, 3, some sort of subgroup of those. And that's it for this one. Yay!